Hi everyone, welcome to the 2020 MIT Uncertainty Quantification Workshop, or the 2020 MUC Workshop. Thank you for bearing with us as we figure out virtual options for this workshop given the coronavirus outbreak, which unfortunately made us have to reshuffle our plans. So my name is Andrew Davis. I apologize if any of this is redundant information given previous welcome addresses or welcome hello things that people have sent out since we're pre-recording this. But I'm just going to jump right in. Um, so let's start with what Muck is. So Muck is, as you all know, hopefully, given that you're here, a software package that is specifically designed for uncertainty quantification. It is primarily written in C++, but it is callable from both C++ and Python, meaning that we have a Python wrapper around the C++ capabilities. And the wrapper, or at least at a very high level, using Muck from either C++ or Python should be pretty much the very similar, except for some obvious syntax differences because those are very different languages. So in this workshop, we're going to be focusing on using the Python wrapper. In this workshop, we're going to be focusing on two specific features in Muck. The first is building models, graph-based modeling specifically. We're going to be building both physics-based models or physical models, and also probability distributions and probability densities using these graph-based techniques that Muck relies on very heavily. And then we're also going to be applying or using that within a Bayesian inference problem, which we're going to solve or at least sample from some sort of distribution using MCMC. So those are don't even begin to cover all of the capabilities within Muck, but unfortunately in a 1 or 2 day workshop, we don't have time to get into everything. So just here's a list that I don't even think is completely comprehensive, but some of our other big capabilities include, so graph-based modeling and MCMC, of course, are the two that we're going to be focused on. Polynomial chaos expansions, Kahoot and Louvre expansions, which is bolded because we are going to be using KL expansions in one of our examples. And then also Gaussian processes, transport maps, which is basically these maps between two probability distributions, regression, including polynomial regression and Gaussian process regression, surrogate modeling, specifically surrogate modeling within algorithms such as MCMC. And if we have time, we will get into that a little bit in this workshop. And also optimization. Muck has some internal optimization tools, but also has a wrapper around NLOpt, which is an optimization package. Also, we have a really slick HDF5 interface on the C++ side that is trying to mimic HDF or H5Py on the Python side, which isn't really an uncertainty quantification technique, which is why I didn't list it here, but it is a really nice feature in Muck, so I figure I'll mention it. So a brief history of Muck, where we are, who we are, what we came from. So Muck started around, I think around 2012, and has been under continued development since then. Muck is an open source object-oriented code, so that means that anybody can download it, anybody can use it, anybody can contribute to it, and then the object-oriented side is mostly just because we're using C++ and Python. So originally Muck was developed by a team of graduate students in the uncertainty quantification group at MIT, myself included, and the whole idea was that I'm going to get rid of this, sorry. So the whole idea was that we were developing a lot of the same code across multiple people, and so to minimize effort across the team, or minimize the amount of duplicated effort, I should say, and to minimize bugs, we figured we would share our code in a cohesive package, which has since grown into Muck. We have expanded this to an international team, primarily across universities and national laboratories. And as I said, we are completely open source, so we are always open to more users and more developers. And our goal is to build a strong community of users and developers So we appreciate any contributions anybody has. And our website, of course, is at muck.mit.edu. So the goal of this workshop is to learn graph-based modeling within Muck. I already kind of mentioned these, but I'm going to say it again. We're going to do Carhoon and Louvre expansions, which will give us a Gaussian random field. And then we're going to try to do some Bayesian inference specifically with MCMC or Markov chain Monte Carlo. If that means nothing to you, that's fine. We're going to go through all of that in much, much more detail over the next day or two. So I will leave it to the future for you to learn what that is. If we have time, hopefully on the second day, we're going to be covering some advanced topics, specifically multi-level MCMC and surrogate modeling within MCMC. And then local approximation MCMC is using a continually refined surrogate model, which you develop on the fly as you collect samples within MCMC. Again, if that means nothing to you, don't worry about it. We'll get there, hopefully. So a motivating example, this is going to be the simple toy example that we use throughout the workshop, where we're just going to be learning some sort of conductivity field, kappa, which is going to appear in this Poisson equation, this ODE here, where we're going to be given data, which is going to be some prescribed true kappa, where we'll solve for the solution U, and we will add some noise, and that'll give us this data. Which we will then use to then infer back the true kappa and see how good we can do or how well we can do. So this kappa we're going to be modeling as a Gaussian random field. We're going to decompose it using a KL expansion. We'll sample realizations of that random field and then evaluate the model, which is kind of the forward uncertainty quantification process, or Monte Carlo. And then we're going to prescribe a true conductivity field, and we're going to infer that field using noisy data, which is going to be the Bayesian inverse problem. So before we get into that, I wanted to open with an example of a slightly more complicated, although not that much more complicated model, just to kind of say that this isn't just a mathematician having fun with the Poisson equation, that these actually do come up in practice, that these types of problems actually do come up in practice. So this tracer transport problem, so you can imagine this is going to be some sort of aquifer. It's a still pretty idealized case, so imagine a square aquifer. Each one of these regions, I guess you could have some sort of mapping from a non-square aquifer, but regardless, imagine this aquifer. Each one of these regions would correspond to like a different soil property, so clay, bedrock, gravel, that kind of thing. And they're going to have a different transmissivity, which is kind of a conductivity field, which will allow water or whatever's in the aquifer, some liquid, to pass through it. We're going to solve for the steady state hydraulic head, which is what this H is here, using this nonlinear Poisson equation. This nonlinear, you see H times H right here. And that gives us the hydraulic head, which is these colors, or this heat map over here. And then the velocity of whatever fluid, probably water, maybe oil, something like that, is going to be this Darcy velocity, which is proportional to the negative gradient of the hydraulic head. Again, you see a nonlinearity and this transmissivity parameter. And our goal is now to infer the transmissivity, these kappa. There's kind of a second part to this model, where given that velocity field, we have some non-reactive tracer. So the concentration of the tracer, some sort of maybe contaminant that's spilling out of a well, for example, is this C. And we have this tracer, which is going to be advected and diffused around the aquifer. So we have this time derivative. And then the second term here is the diffusive term. So you see this term here is your standard diffusion. This second term, this matrix here, means that the concentration can diffuse along flow lines. And then here is the advective term. The concentration is advecting this tracer around the domain. And then on the right-hand side here, we have some forcing term. Maybe the tracer is being forced out of a well or something like that. So we'll have 125 total observations. In space, we have a 5x5 sensor grid, and we will observe at the same locations at 5 different times. We're going to generate data given some true transmissivity field on a 200 by 200 grid, and then we're going to do our inference problem on a 100 by 100 grid to avoid committing an inverse crime, which is when you use the same mesh to generate the data and also to, the the same mesh to generate the data and also do the inference. All right, so yeah, so given that data, so observations of this tracer, we're going to be inferring the transmissivity field. And so what we do is we prescribe some sort of prior information, which is a uniform distribution in this case. The uniform distribution for each one of these, so there's 6 parameters, and you'll see these are the 1 and 2 dimensional marginal distributions. The prior information is a uniform distribution. So in this case, this top marginal right here, uniform distribution from -1 to 0, here from -1 to 1. And then given data, we're going to update that distribution to the posterior distribution, which is plotted here, or the 1 and 2 dimensional marginals of the posterior are plotted here. And you can see any structure that's not a uniform distribution is something that we've learned from data. So in this case, this bottom parameter here, we've learned quite a bit of information about the parameter. Maybe this parameter we haven't learned quite as much. These 2 parameters, so kappa 4 and kappa 6, are very tightly correlated, so there's a lot of correlation structure, and you can see this is clearly a not Gaussian, very complicated distribution, which we were able to sample using MCMC. So the forward model in this case, so that physics-based model that I just presented, costs about 13 seconds per serial evaluation. We're able to reduce that cost for something like 3 to 4 seconds by implementing it using some parallel capabilities. This gray curve, each light gray line is one MCMC chain, or Markov chain Monte Carlo chain, which you can see that and then this darker curve here is the expected error, so the average of all of these different MCMC runs. You can see this is quite expensive, maybe not completely prohibitive, but it is prohibitive. If we replace that surrogate model with if we replace that forward model with a surrogate model, in this case, we're using a local polynomial approximation. That's where we get these red curves, and you can see you can get similar error reduction, or similar errors using significantly less runtime, which is a nice thing. So we're going to be talking a little bit about this local polynomial surrogate technique on the second day, but you can see that we get about an order of magnitude improvement in the runtime, and the longer you run your chains, the more the improvement. So again, more details on that to come, but it's a nice motivation for you, hopefully. So just in a quick summary, as I said, Muck is an open source software package for uncertainty quantification. In this particular workshop, we're going to be focusing on graph-based modeling and Bayesian inference, although Muck has many, many other capabilities, which we're happy to talk about offline, or you can ask questions to the group if you want. Currently, Muck is still under active development. We're coupling Muck with other software packages such as Phoenix, Hippie, and DL2, which do finite element methods and forward modeling. And we're also coupling Muck with UQTK and Dakota, which are other uncertainty quantification packages, to try to kind of combine those efforts, or at least make them accessible from one to the other. Yeah. On a more theory perspective, we're also working on developing methods for common filters, neural nets and machine learning techniques, computing transport maps with a Wasserstein distance, and many other things I'm probably missing because the number of developers is quickly increasing. So again, we're happy to put you in touch with people who are currently developing Muck. And again, new users and developers are always welcome. So if you're all interested in using or developing Muck, please let us know. We're happy to talk more about it. So enjoy the workshop. Thank you for bearing with us with this virtual workshop, and hopefully you get a lot out of it. Thanks.